Hello, sixth graders. We are continuing our probability unit today with sample space and fundamental counting principle. Learning target. I can find sample space and probabilities by using tree diagrams and the fundamental counting principle to determine total outcomes. Write this down in your notebook or get your note packet ready. All right, we have a vocab here, vocab word that we need to write down, sample space. The set of all possible outcomes or results in an experiment. So this is everything that could potentially happen. So if we were flipping a coin, the sample space would be heads and tails. That's what's possible. If we're rolling a six-sided dice, the sample space would be 1, 2, 3, 4, 5, 6. There's two methods that we're going to learn about to find sample space. One of them is tree diagrams, and one of them is fundamental counting principle. So again, sample space, that's all of the possible outcomes in a situation. So here we have a vendor that's selling vanilla and chocolate ice cream. The customers can choose from a waffle or sugar cone and either hot fudge or caramel topping. We're trying to find the sample space for all possible orders if they were to pick one scoop of ice cream, one type of cone, and one topping. So this is a table. It's a little different than what a tree diagram looks like, but it still makes all of the possible outcomes. And if you look here, the first thing is that we are choosing either vanilla or chocolate ice cream. Then, depending on the type of ice cream, we are picking the cone. So if we chose vanilla ice cream, we have the choice between a waffle cone or a sugar cone. If we chose chocolate, again, we can still pick either a waffle cone or a sugar cone. Then, depending on the type of ice cream and the type of cone, we could then pick whether we want hot fudge for the topping or caramel for the topping. And that's all of the potential outcomes. So I could pick vanilla ice cream with a sugar cone and caramel, or I could pick chocolate with a waffle and hot fudge, but all of these are the outcomes. To figure out total outcomes, we would count everything that's over here, which if I go through and count 1, 2, 3, 4, 5, 6, 7, 8, there are 8 outcomes or 8 different types of orders that you could do where you are picking one scoop of ice cream, one cone, and one topping. So again, this is a table. We'll learn about making tree diagrams on the future slides. Okay, so we're looking at an animal shelter that has both male and female Labradors, and they come in yellow, brown, or black. And we are trying to find the sample space of all possible labs at the shelter. So looking at this situation, there's 2 things to pick from. We are either picking, let me change color here. You would either get a male or a female dog. And then depending on what gender you get, you would either get a yellow lab, a brown, or a black lab. So when we're making our tree diagram, starting with that first situation, you would pick either male or you would pick female. Okay, so we write them both down. Now, let's say I chose a male Labrador. Ask yourself then, what's the next thing? What colors could you pick? You could either get a yellow lab, you could either get a brown male lab, or you could get a black lab. What if you chose female? Well, if you chose female, you could get a yellow female, a brown female, or a black female. Okay, so this is our tree diagram, starting with the top ones, and then what you branch out from there. So now, thinking about it, I could have picked a male yellow lab. That's one outcome. I could have picked a male brown lab, which is a second outcome. I could have chosen a male black lab, which is 3. I could have picked female yellow lab, a female brown, or a female black lab. So that means there are 6 total outcomes at this shelter. So you're just counting what's down here at the bottom in order to figure out total outcomes. Okay, so you start with the different events. So you're picking male or female, and then the different color, and it just branches out in a tree from there. Okay, you also, since this is usually a common question, you could have flipped it around. You could have said the different colors first, yellow, brown, black. If you chose a yellow lab, you could have gotten male or female. A brown lab, you could have gotten male or female. And a black lab, you could have gotten male or female. And then again, if you count 1, 2, 3, 4, 5, 6, you still get the same answer. You do not count the top part. You only count the outcomes down at the bottom. Because when you count this male here, it's already including the yellow up above. And when you count this female, it's already counting the yellow up above. So if you count them again,
it's a duplicate. So you only count what's at the bottom.
Now we're making a tree diagram for this car situation. A car comes in silver, red, or purple, and it either comes as a convertible or a hardtop. How many different combinations of cars are there to choose from? So if I'm thinking about this, the things that I'm doing or the situations, there's two events happening. I'm picking a color between silver, red, and purple, and then I'm picking either convertible or hardtop. So when I'm making my tree diagram, I'm going to start with the color options. So I could pick silver, I could pick red, or I could pick purple. Then after I've chosen my color options, I then either pick convertible or hardtop. So let's say I chose a silver car. From silver, I could get convertible or the hardtop. If I chose a red car, I could have picked convertible or hardtop. If I picked a purple car, I could have picked convertible or hardtop. Okay, so there's my tree diagram, each of the colors and then the type of top on the car. Again, when we're counting for total outcomes, we only include the bottom. So 1, 2, 3, 4, 5, 6. So there are 6 outcomes or 6 different types of cars that I could pick from. And then again, do not include the stuff on the top, the colors silver, red, purple when we're counting, because that's already included in the types of tops to the car. The next question here says, what is the probability of choosing a purple convertible? So if I look at my tree diagram and find all of the ones that are purple and convertible, well, there's one right here. That's the purple car with a convertible top. That's only one outcome. And remember, when we write probability, we write it as a fraction out of the total possible outcomes, which there are six of them. So if I were to pick a car at random, I have a 1 in 6 chance that it's going to be this purple convertible.
All right, another one we're going to make tree diagrams for. At the deli, I can choose from the salad bar, wing bar, or soup bar. I can get a bun or a breadstick. And then for dessert, I can select pudding or a slice of pie. And then what are all of the combinations of meal options and how many outcomes are there? So looks like now we get 3 things that we're choosing from. We can choose salad, wing, or soup bar. And then the next thing would be choosing bun or bread stick. And then for dessert, we either get pudding or a slice of pie. So starting with that first choice, there was salad bar, there was wings, or there was soup. After I have chosen which type of food item I want, then for each of them I get either bun or a breadstick. So if I chose the salad bar, I could then choose bun or the breadstick. Just abbreviating again. If I chose the wing bar, I could have gotten a bun or I could have gotten a breadstick. If I chose the soup bar, I could have gotten bun or breadstick. Okay. Then after that, I have to pick dessert. So let's say I chose salad and a bun. Then I would need to choose either pudding I'll have to write these out since they both are similar spelling. Or I could have picked pie. If I chose salad with bread stick, then I could have picked pudding or pie. If I chose the wing bar with the bun, I could have picked pudding or I could have picked pie. If I chose the wing bar with the breadstick, I could choose pudding or I could choose pie. Okay, it's kind of continuing on. Are you noticing a pattern? Okay, if I chose soup with a breadstick, I could have chosen pudding or a pie. Now we have 3 layers. We only, again, count the very, very bottom because when you count this pudding right here, that is also including this bun and this salad. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is 12 outcomes. So there's 12 different meals that I could have picked. Then we have a probability question here. What is the probability of having salad bar in my combination? Okay, so the salad bar is here. So I could have had salad bar bun with pudding, that's 1. Salad bar bun with pie, that's 2. Salad bar breadstick pudding, 3. Salad bar, breadstick, pie, that's 4. So I would have to choose all 4 of those for those questions because any of them include the salad bar. So that's 4 out of the 12 total, which would be 1/3. All right, Marcos tosses 3 coins. If all 3 coins show up heads, then Marcos wins. Otherwise, Kara wins. First, we need to find the sample space. Then we're trying to find the probability that Marcos wins. So he's tossing a coin 3 times. The first time that he tosses the coin, he could get heads or tails. Now he's on to the second flip. He got heads the first flip. He flips the coin again. What could he get? Well, he could get heads or he could get tails. Let's say he flipped tails the first time. Well, then when he flips the second time, he could get heads or he could get tails. If he got heads the first time, heads the second time, he flips the third time, he could get heads or tails. Flips heads the first time, tails the second time, the third time, he could get heads or tails. If he flipped tails the first time, heads the first or the second time, then he could get heads or tails on the third flip. Tails the first time, tails the second time, and then he could get heads or tails on the third. Okay, so this was the first flip, the second coin flip, and the third coin flip. To figure out total outcomes, we would then count the bottom. 1, 2, 3, 4, 5, 6, 7, 8. 8 possible, I keep spelling this wrong, outcomes. Now the question, find the probability that Marcos wins. Well, it told us that he would need to have heads show up all 3 times. Well, I see that right here. Heads, heads, heads. Otherwise, I don't see that again. So that's only 1 out of 8 possible outcomes. So he has a 1 in 8 chance that he would win. Otherwise, Kara wins. It's a lot more likely Kara's going to win. Okay, now the fundamental counting principle. This is another way to find total outcomes without having to make tree diagrams. So write this down here. This is like the rule or the how we find it. So if event 1 has m possible outcomes, m being a number that we would plug in depending on how many outcomes there are, and event 2 has n possible outcomes, again plug in a number for n, then event 1 followed by event 2 has m times n possible outcomes. So what it's saying is you take the outcomes of one event and you multiply it by the possible outcomes of the second event, and that would tell you the total possible outcomes. So we're trying to find the total number of outcomes when a coin is tossed and a number is rolled. So I always ask myself, how many events are happening? Looks like 2. We're flipping a coin and we're rolling a cube. Thinking about a coin, how many possible outcomes are on a coin? Well, I could get a heads or I could get tails. That's 2 outcomes. A number cube, as in a 6-sided dice. Well, I could roll a 1, 2, 3, 4, 5, or a 6. That's 6 possible outcomes. So now I multiply those 2 numbers together. 2 times 6 equals 12 outcomes. If I had made a tree diagram, I would again find the exact same thing, that there's 12 possible outcomes. So this is a great way to be able to check that your tree diagram is correct. The only thing with this, if it then asked you a probability question, it's a little bit more tricky to find out because you don't have that visual to help you figure out all of the outcomes. All right. Excuse me, a couple more here. Find the total number of outcomes when choosing from bike helmets that come in 3 colors and 2 styles. So you're doing 2 things. You're choosing a color and you're choosing a style. There's 3 colors, 2 styles. Multiply them together, which is 6 outcomes. The jean shop sells young men's jeans in different sizes, styles, and lengths as shown on the table. Find the number of jeans available. So you're choosing a size, a style, and a length. Looking at the size, there's 1, 2, 3, 4, 5 sizes to choose from. For choosing a length, there's 1, 2, 3 lengths. And then for style, we've got 1, 2, 3. Multiply those together. 5 times 3 is 15 times 3, which would be 45 outcomes. Then it says find the probability of a 32-34 slim fit. Well, since it's picking one of each of those, that's only one outcome out of 45 total outcomes. So you have a 1 in 45 chance that it would be 3234 slim fit. Okay, just two more that I want to go through, and we're going to use tree diagrams for these. And then we'll also show fundamental counting principle. So we're flipping a coin 3 times. So when you flip it the first time, you could get heads or tails. When you flip the coin a second time, you could get heads or tails. If you flip tails the first time, when you flip it the second time, you could get heads or tails. If you flipped heads and the first time, heads on the second time, the third time, you could get heads or tails. Same thing, if you did heads, tails, you could get heads or tails. And same thing here. So total outcomes 1, 2, 3, 4, 5, 6, 7, 8. So 8 outcomes. Now, if we were to use the fundamental counting principle for this one, you're flipping 3 coins. So you have 3 different events. 1, 2, 3. When you flip the coin the first time, you could get heads or tails. Flip it the second time, heads or tails, that's 2 outcomes. The third flip, you could get heads or tails, 2 outcomes. And then you multiply them together. Well, 2 times 2 is 4, times 2 is 8. So again, 8 outcomes. I just wanted to show you that both ways work. Okay. Now this one always throws people off here. So we are rolling a dice 2 times. Okay. The first time you roll the dice, what could you get? Well, you could roll a 1, a 2, 3, 4, 5, or 6. Now you're on to the second dice. If you rolled a 1 on the first dice, what could you roll on the second dice? Well, you could roll another 1, or you could roll a 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, or a 6. Let's say you rolled a 2 the first time. You pick that dice up and you roll it again. Well, you could get a 1. You could roll a 2, a 3, 4, 5, or you could roll a 6. Let's say you rolled a 3 the first time. Are you noticing a trend? Whatever you roll on the first time, you could roll that same number again on the second time, and that always seems to kind of throw people off. But if you rolled a 3 the first time, you could roll a 1, 2, 3, 4, 5, or a 6. If you rolled a 4 the first time, you could roll a 1, 2, 3, 4, 5, or 6. If you rolled a 5 the first time, when you pick it up and roll again, you could get a 1, 2, 3, 4, 5, or a 6. If you rolled a 6 on the first dice, when you pick it up and you roll for the second time, you could get a 1, 2, 3, 4, 5, or a 6. Counting the outcomes, remember you just count the bottom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So there's 36 outcomes. If we had done the fundamental counting principle, you're rolling a dice 2 times. That's 2 events. The first roll, you could have 6 outcomes. The second roll, you could have 6 outcomes. Multiply that together, 36 outcomes.
The last part here, the you do, these should be at the bottom of your notes. There's 3 questions here for you. Read them closely. Make sure you complete all parts of the questions. I will be looking for these in your notes. And then bring your notes to class with you.